everybody. Welcome back to Environmental Science Analysis with Dr. Lisa. Today we're going to talk about some time series analysis. I gave you a YouTube video on time series analysis, and it showed some examples, and it was doing things like sales and website visits and stock prices. And those are all things where the data is quite well defined, and stock prices are measured in nanoseconds every day. You have very clean data. There's not usually any data breaks or any problems like that. In the environmental field, that's much, much less common, right? In the environmental world, like the real world, there's all kinds of things that can go wrong with the data itself and how it was collected. Sometimes we have the greatest intentions, but our samples just don't get collected for various reasons, or they fail, or something happens. So I'm going to show you how to do a time series analysis with some messier real-world data. So the first thing we'll do here, of course, is load up our libraries like we always do, and then we're going to load in our data here. So here's data. This is NB, stands for New Brunswick. So if I open this up, this is data on PCBs, polychlorinated biphenyls, measured in the air in New Brunswick, where Rutgers University is, over at the experimental farm. And this is the PCB concentration measured in the air in picograms per cubic meter. This is the date. This is formatted the way Excel formats the dates. So it's a long number. It's the number of days since December 31st, 1899, I think it is. And then here's the temperature, the average temperature on that day in degrees Kelvin. So over here in the last three columns, I've converted the date into the number of days since day 0, the first day of sampling. I've calculated the inverse of the temperature, 1 over the temperature in Kelvin, and I took the natural log of the PCB concentration. So that's our data. And you can see there's actually quite a lot of measurements here, about over 200 measurements. So this is actually a pretty large data set compared to some of the data sets I've had to deal with before. So here's our New Brunswick time series. So we've loaded that up. I'm going to attach it. There you go. And then let's just plot our data points. So here's the data points. Here's the number of days since day 0 when we started collecting these samples. And here's the concentration in picograms per cubic meter. And you can see, first of all, there is a periodicity here. Concentrations go up in the summer and down in the winter. We think that this is because PCBs, like a lot of organic chemicals, are driven by temperature. When the temperature is higher, more of them evaporate and get into the gas phase. So there's a periodicity here. The other thing you notice is that there's some data gaps. We ran out of funding. We didn't collect data for a while here. Another data gap over here. So not perfect data. And the other thing you notice is that it does seem like there's a trend where concentrations are going down over time. They were high back here in the early period, but they did seem to go down. So we want to capture that. We want to try to calculate how fast are they going down. Could we maybe express that in terms of a half-life or something like that? So the other thing I'm going to do here, I'm going to plot a histogram of this data. And notice, here's my histogram. This is the frequency, and this is the concentration. Most of the concentrations are on the low end, so they're stacked here on the left side. And this is a very characteristic histogram of a not normal distribution. In fact, this is a log normal distribution, and I can prove that to you by plotting the histogram of the natural log of the PCBs here. And here it is. You can see now it looks quite symmetrical. Now it looks like a Gaussian, bell curve. That's very typical. That's what happens when you have a log normal distribution. If you take the log of it, it becomes a normal distribution. So that's just something to keep in mind as we go through here. The first thing I'm going to do is do a model where I use both time and temperature to predict the PCB concentrations. And I'm going to do this as a linear model. I'm going to use the LM command here for a linear model. The data comes from this thing called New Brunswick. And my model is the natural log of PCBs is a function of the inverse temperature and the number of days. Okay, this is basically using the Clausius-Clapeyron model. Not that that means anything to you. But again, the natural log of the PCBs is a function of the inverse temperature and the number of days. And so I'll run that model, and then I could run the summary of that model, and here you go. Here's my inverse temperature, and here's number of days. This is the coefficient for the days, and so this is the time constant, And notice it's negative, which means that the concentration is going down over time. And notice over here, it is highly significant. That's what the 3 stars and this very, very low p-value stand for. It turns out the temperature is also highly, highly significant here, and so is the intercept, not that that matters. Okay, so that works just fine. And so let's go ahead and plot our data again here. And then I'm going to just, this para LWD equals 2 is just to make the lines a little thicker because otherwise they're hard to see. That's line width. LWD stands for line width. And so now I'm going to add a line to this plot. Here is my predicted concentration. It's predicted as a function of temperature, so it's spiky. You know, it changes a lot depending on how the temperature is fluctuating. And it does a reasonably good job of matching the data. Notice it doesn't capture the really high concentrations. We could talk about ways to adjust the model to try to do that, but this is a consequence of having log normally distributed data. The really high concentrations can be very hard to model. Okay, so this was using a multiple linear regression to do our time series, and you can totally do that, nothing wrong with it. But you can also use a nonlinear model, and for that we're going to use the NLS command here. So I'm going to call this my simple model of time and temperature, so I'm going to call it simple.model. And I'm going to use the NLS, the nonlinear curve fitting routine. And in this, I'm going to be using the actual PCB concentration, and then within the R software, I'm going to take the log of it. When you use the command log in R, you're getting the natural log. If you want a base 10 log, you have to use the command log 10. Okay, so this is going to be the natural log of the PCBs here is a function of my slope term A divided by the temperature in Kelvin, no longer the inverse temperature, the temperature in Kelvin, plus B times the number of days plus C. Okay, so that's my model. And if you're going to use this NLS command, it's a good idea to give it a starting point for your 3 coefficients here. I've called them A, B, and C. You can call them whatever you want. I give them a reasonable value for starting out. And I control enter, run that. And then here's my summary. And if you are very wise, you notice, here's my time coefficient minus 4.338 times 10 to the minus 4. And the first run that we did here, minus 4.338 times 10 to the minus 4 when we use the nonlinear model. So in this case, it doesn't matter one bit whether you use the linear model or the nonlinear model. You're getting the same thing. Okay, so that's your summary. Then let's do a plot now. And if we've done everything right, it should look exactly like this plot, right? Because all the coefficients are the same. So let's run this, and lo and behold, yes, it looks exactly the same. We've just generated the same model result using a nonlinear model instead of a linear model. It's all good, doesn't matter. Now, another way that we could do this is by saying that the periodicity here is not due to temperature, but due to season. And so we could use this model. This is from that paper that I posted on the Canvas website. It's by Venier et al. From 2012. It's called Different Time Models. And this is where the log of PCBs here now is going to be a function of the sine of this parameter z times the number of days. Okay, so here's z. Z is defined as 2 times pi divided by 365.25. Okay, and what that's saying is that this fixes the periodicity as 1 year. You get 1 maximum and 1 minimum per year. Okay, that's what the 2 pi is for. If you just had a pi, a sine curve normally would give you 2 maxima. And the 365 obviously sets it to days, 365 days. So that sets your periodicity, sorry. I hate that. This sets your periodicity to exactly 1 year. Okay, so we're going to define this thing that I'm calling Z, Z-E-E. Okay, and by putting it here in my model, I'm saying that I'm going to use both the sine here and the cosine of the number of days multiplied by Z, just to see whether there's, different things going on here. And the coefficient, E or F in this case, will decide when the maximum is. What day during those 365 days represents the maximum day? Could be anywhere. If this was a current use pesticide, the maximum might occur when it's applied, which might be, the beginning of spring, like maybe in March or something. It's a pre-emergence herbicide. If it was something that had a lot to do with forest fires, it might max out in August or September when things are dry and forests tend to burn. It could be any time of the year, and that's what this coefficient is going to allow us to determine. And then here we have g times the number of days. That will give us our time constant. And then h is just an intercept term that I've added in here. And again, as I always do when I use the nonlinear model, I give it a reasonable guess. I mean, this isn't even a very good guess, but at least some guess of what the coefficients should be or could be. So we'll run that. And I can summarize it here. And again, here's my time constant. Minus 4.98 times 10 to the minus 4. If you were paying close attention up here, we got minus 0.4338 times 10 to the minus 4. So it's a little bit different. Highly significant here. But notice f, which was related here to the cosine of the number of days, f is not significant. So we should probably take that out, right? But just for kicks, first let's plot this. Okay, so that's what the function looks like when we're using the sine and the cosine. It's much smoother because it's no longer dependent on the day-to-day variation in temperature. So a much smoother line, still capturing the data pretty well. And then we could figure out the half-life. I'm going to call it season.half is the log of 2 divided by the coefficient in the seasonal model. And then that's going to give me, you notice over here, it's giving me the log of 2 divided by all the coefficients, all 4 of them. But if I want to print this out here, I would just be printing the third coefficient, which is my g here. So the half-life in days is 1,392 days. Okay, and then if I divide that by 365.25, I could get my half-life in years is 3.8 years. Okay, so that's my half-life. How long it takes my concentrations to drop by half. So we've seen here that the one of these parameters, f here, which had to do with the cosine of the number of days, this was not significant. So let's do this over again by taking that out. So now we just have the sine here. Here's the time constant, and here's my intercept. So I'm going to call this modified seasonal model, mod seasonal model. I'm going to run that and also run the summary on that. Here's your summary. Now everything is significant here because we got rid of that one parameter that was not significant. The time constant has changed a little bit. It's now a little bit larger in magnitude, minus 5.037 times 10 to the minus 4, slightly different than it was before. So we can plot that. It's probably not going to look a whole lot different. I don't know if so take a close look at this, and then we'll hit enter, and it didn't change much, but just a little bit of a change here. There's the modified seasonal model. I could print out the coefficients from that here. So now I'm getting a half-life of minus 0.378. The minus just means it's declining, so the half-life is about 3.767 years, okay, whereas up here, the half-life was 3.8. So just ever so slightly shorter half-life, faster decline, shorter half-life. Okay, now we could ask ourselves, first of all, let's put it all together here. And here you can see the two different models plotted on the same thing. Where we use temperature is in the green, and where we use that modified seasonal model is in the blue. You can argue all day long about which one is a better fit just by looking at it visually. But if we really want to know which model is best, we might do that by calculating the AIC of each model. And here you go. The simple model has an AIC of 401, and the modified seasonal model has an AIC of 397. Lower AIC is better, so the seasonal model is actually working a little bit better. So that's two different ways of doing the time series analysis, either doing it as a linear function or a nonlinear curve fit. Either way, you can do all kinds of fun things with this. You can mess around with the periodicity. You can do all kinds of interesting stuff. But that's just an example of how you can do time series modeling in R.